In the previous module, we have provided an example of the fact that product of normal spaces may not be normal. What we have done? We have taken RL cross RL and taken a closed subspace of RL cross RL and shown that the closed subspace is not normal, but we have done the proof by taking two arbitrary closed set, but we have not taken two concrete closed sets in L. Next, we shall produce an example which will be much more concrete example to show that product of normal spaces may not be normal. We also introduce another separation axiom to end this section. Let us go to slide presentation. In this discussion, first, as promised, we shall provide an example of the fact that product of normal spaces may not be normal. We shall use the ordinal spaces. Let us consider the well ordered set S omega plus 1 with the order topology, and also consider the subset S omega in the subspace topology. We have earlier told that S omega plus 1 is equal to S omega union singletoned omega. We wish to show that S omega plus 1 Cartesian product S omega is not normal. In fact, this example is taken from the book of Moncrief. This is a famous example in the literature called Tychonoff plank. Let us first consider the space S omega plus 1 Cartesian product S omega plus 1 as if this is a square. Now consider its diagonal del is equal to x x such that x belongs to S omega plus 1. We know that all linearly ordered topological space is Hausdorff, and therefore S omega plus 1 is also Hausdorff. Since S omega plus 1 is Hausdorff, therefore del, the diagonal, should be closed in S omega plus 1 Cartesian product S omega plus 1. In fact, if u and v are disjoint neighborhoods of x and y, where x not equal to y, then u Cartesian product v is a neighborhood of x y which does not meet the diagonal del. Therefore, in the subspace S omega Cartesian product S omega plus 1, the set A is equal to del intersection S omega Cartesian product S omega plus 1, which is the diagonal del deleted the top point omega Cartesian product omega, which is closed. In fact, in S omega Cartesian product S omega, we can think it as a square where the right side vertical edge is absent. Similarly, the set B is equal to S omega Cartesian product omega is closed in S omega Cartesian product S omega plus 1. What is S omega Cartesian product omega? In fact, this is the top horizontal edge. Then we get two disjoint closed sets A and B. Now we shall show that these two disjoint closed sets cannot be strongly separated by disjoint open sets. If possible, we can separate A and B by disjoint open set. That means there exist disjoint open sets U and V in S omega Cartesian product S omega plus 1 containing A and B respectively, from which we shall derive a contradiction. Given x belongs to S omega, consider the vertical segment x cross S omega plus 1. We assert that there is some point beta with x greater than beta less than omega such that x beta lies outside U. For if U contains all points x beta for x less than beta less than omega, then the top point x omega of the vertical slice would be a limit point of U, which is not possible because V is an open set disjoint from U containing the top point. So, choose beta x to be such a point. Just to be definite, let beta x be the smallest element of S omega such that x less than beta x less than omega and x beta x lies outside U. Let us define a sequence of points of S omega as follows. Let x1 be any point of x omega. Now consider x2 is equal to beta of x1, and by induction we define xn plus 1 is equal to beta of xn. Thus, we have a sequence x1 less than x2 less than x3 and so on. Because beta x greater than x for all x, we get the inequality. The set xn is countable and therefore has an upper bound in S omega, as we have proved earlier. Now let B belongs to S omega be its least upper bound. Because the sequence is increasing, it must converges to its least upper bound. Thus, xn converges to B, but beta of xn plus 1 is equal to xn plus 1, so that beta of xn converges to B also. Therefore, we have the sequence of ordered pairs xn beta xn converges to the point BB in the product space. This gives us a contradiction, for the point BB lies in the set A, which is contained in the open set U, and U contains none of the points xn beta xn. Next, we will enter to some deeper properties of normal spaces. We have already told that we shall prove that every regular second countable space is metrizable, which is called Eurytion metrization theorem. But to prove it, we must require some preliminaries. Before that, we use another important theorem which says that every regular second countable space is normal. As we told, we shall next prove the following theorem. Every regular space with countable basis is normal. An immediate application of above theorem, we can say that real line with usual topology is normal. Of this theorem, let X be a regular space with a countable basis. Say script B is equal to Bn such that n belongs to capital N. Let capital A and B be two disjoint closed subsets of capital X. The idea of the proof is to cover A with some basic open sets and to cover B with some basic open sets, and then to eliminate the overlapped parts. Each point x of A has a neighborhood capital U not intersecting B. This follows from the regularity property of capital X. Also, using regularity property, we can choose a neighborhood V of X such that X is contained in V and V is contained in its closure, which is contained in U. We can do these operations by taking elements from B also, because we have already told anytime we can replace open set by basic open sets. So, by choosing such basic element for each x in capital A, we can construct a countable covering of capital A by open sets whose closure does not intersect B. Since the covering of A is countable, we can enumerate them. Let us denote it by UN. Similarly, we can choose a countable collection Vn of basic open sets covering B such that closure of Vn disjoint from A from each n. This sets U is equal to union of U n and V is equal to union of V n are open sets containing A and B respectively, but they need not be disjoint. We shall perform the following simple trick to construct two open sets which are disjoint and should cover A and B. Given n, let us define U n dot is equal to U n minus union of V I is equal to 1 to n, and similarly we define Vn dot is equal to Vn minus union of ui bar I is equal to from 1 to n, where ui bar is the closure of u and vi bar is the closure of v. Then each un dot and vn dot are open sets, because union of vi bar I is equal to 1 to n being finite union of closed set is closed, and difference of an open set minus a closed set is a open set. Now, it is easy to observe that un dot is a cover of A and Vn dot is a cover of B. The collection un dot is a cover of A because each x in A is in A belongs to un for some n, and x belongs to none of the sets Vi. Similarly, the collection Vn dot covers B. Now, let us set u dot is equal to un dot, where n is equal to from 1 to infinity, and v dot is equal to Vn dot, where n is equal to from 1 to infinity. It just remains to show that u dot and v dot are disjoint. In fact, if x belongs to u dot intersection v dot, then x belongs to u j dot intersection v k dot for some j k. Suppose that j is less than k. It follows from the definition of u dot that x belongs to uj, and since j less or equal to k, it follows from the definition of vk dot that x does not belongs to uj bar. A similar contradiction arises if j greater or equal to k. Hence, u dot and v dot are disjoint, and u dot contains A, v dot contains B. So, we have completed the proof of the theorem. If we closely look the proof of the theorem, then we can observe that we have used the countable covering of A and B, nothing except this. So, somehow if we can get countable covering of A and B, then we can follow the same procedure as in the above proof. Keeping this in mind, we state the following theorem: every regular Lindelöf space is normal. So, we can prove this theorem exactly as the above theorem, as I have told earlier. Next, we shall introduce another notion of separability. A topological space X is said to be completely normal if every subspace of it is normal. Clearly, R is a completely normal topological space because every of its subspace is normal. Let us present a equivalent criteria of being completely normal. A topological space is completely normal if and only if every pair of separated subsets can be separated by neighborhoods. Proof: Suppose A and B is a pair of separated sets, then y is equal to x minus A bar intersection B bar is an open subset of X that contains both A and B. Now we have the following equality: closure of A in Y intersection closure of B in Y equal to Y intersection closure of A in X intersection closure of B in X, which is equal to empty set. Thus, closure of A in Y and closure of B in Y can be separated by open neighborhoods in Y. Since Y is itself open, these neighborhoods are also open in X. This proves one part of the theorem. Conversely, take a set Y subset of X and two disjoint subsets A, B subset of Y closed in Y. Now, closure of A in X intersection B is equal to closure of A in X intersection Y intersection B is equal to closure of A in Y intersection B is empty. Similarly, we can show that closure of B in X intersection A is empty. Therefore, A and B can be separated by neighborhoods in X and their intersection with Y separate A and B in Y. This completes the converse part of the theorem. Next, we will discuss about some questions on completely normal spaces. First question: does every subspace of completely normal space is normal? Let Y be a subspace of completely normal space. Then any subspace of Y is a subspace of the completely normal space capital X, and therefore it is normal. This means that Y is completely normal. So we have that every subspace of completely normal space is normal. That means complete normality is a hereditary property. Next, we shall prove that every well ordered set is completely normal in the order topology. We are not going to prove the theorem. This is almost same as we have done in the case of normality. Next question: does RL is completely normal? In fact, we can prove that RL is completely normal. Indeed, the proof of the theorem is extremely similar to the previous example. Both use the fact that there is a basis at X with sets of the form XA, where X is closed, A is open. This shows that every point in a closed set has such a neighborhood that does not intersect the other set. Then coverings by such basis sets are disjoint automatically. So we obtain the disjoint open neighborhoods for any pair of sets such that neither one contains limit points of the other one. Does every metric space is completely normal? Since subspace of metric spaces are metric spaces and metric space is always normal, so every metric space is completely normal. Another question, does every regular space with countable basis is completely normal? Since both regularity and second countability are hereditary property, it can be proved that every regular space with countable basis is completely normal. But the following example shows that product of completely normal spaces may not be normal. In fact, we have earlier proved that RL is completely normal, but RL, Cartesian product RL, is not even normal. In this module, we have discussed an important example of Tychonoff-Planck, which shows that product of normal spaces may not be normal. Then we have proved that every regular second countable space is normal. We can also prove that here second countability may be replaced by Lindelöfness. With this, we end this module. Let us pass to the next module.